welcome you of phenomenal faculty development program organized by VTech iTech Dr. Rangarajan, Dr. Shaguntala Engineering College, sponsored by AICTE Training and Learning Academy. If you believe in yourself and have dedication with determination, you can make numerous publications and patents yourself. Now, I would like to invite Dr. A. Sarvanaraj, Deputy Dean of Project Publication and Patent of VTech iTech Dr. Rangarajan, Dr. Shaguntala Engineering College, to deliver the welcome address. Over to you, sir.
Good evening, again, one and all present here. I take immense pleasure in welcoming you all for the fourth day of our 2-week FDP on waste to wealth, emerging trends in green energy for sustainable development. I'm very much happy indeed to welcome our guest speaker for today's session, Dr. C. Nagendranath Reddy, Assistant Professor from the Department of Biotechnology, Chaitanya Bharati Institute of Science and Technology, Hyderabad. Welcome you, sir.
Thank you, sir.
And our guest is going to give a lecture about biorefineries, current prospects and future perspectives, and about microbial biofuels as well. And it is the need of the hour what the title has been rightly chosen, and it is being presented here for all the participants over here. Recently, in the month of September, our union minister had gone for a visit to US, and he has given a lecture about global clean energy action. And in the lecture, they have created a mission for the innovation roadmap for integrated biorefineries. And this has happened recently in September 2022. And similarly, we are also giving wide exposure about biorefineries and the related areas of research. So I am very much happy, and I take the pleasure in inviting once again our chief guest, who is having enormous experience in this area of research especially. And I'm happy to see one of his paper which has got more than 600 citations, which is on waste biorefinery model towards sustainable circular economy. Congratulations, sir.
Thank you, sir.
We all know how important to us this kind of citations and all. Having 600 plus citations for a single paper in about 4-5 years is a big achievement, of course. And it is not going to stop here. He is going to spread his knowledge, his experience, exposure, whatever he has gained to all the participants attending the program. I am requesting all the participants to be attentive, to be regular, and to show your fullest involvement in this kind of activities what we are taking. Of course, we are taking enormous efforts to make everything happen. And I wish all the participants to have your keen attention to this lecture throughout. Welcome you again, sir. Over to you.
Thank you, sir.
Divya, so you can go for the chief guest introductory.
Yes, sir. Now, I would like to call upon my fellow classmate, Ms. Sangamitra S., to introduce our guest to the participants. Over to you, Sangamitra.
Good evening, everyone. Our dignitary, Dr. C. Nagendranath Reddy, is working as an assistant professor at Chaitanya Bharati Institute of Technology, Gandhipet, Hyderabad. He completed his B.Tech Biotechnology at Satyabama University, Chennai, and M.Tech Biotechnology at SRM University, Chennai. He completed his PhD in Environmental Engineering and Biology at CSIR, Indian Institute of Chemical Technology, Hyderabad. He has 24 publications, 13 book chapters, and 1 blog article. He has attended 2 foreign exchange visits as co-project investigator representing CSIR, Indian Institute of Chemical Technology, as a part of the Indo-Korea collaborative project titled Strategic Biorefinery Platform with Integrated Bioprocess in a Self-Sustained Closed Loop for Multi-Bio-Based Product Output at Kyunghee University, South Korea. He organized many trainings and workshops, such as Biotechnica's 2020 5-day online faculty development program on latest trends and future prospects of biotechnology, an international conference on biotechnology and interdisciplinary technologies. His research interests are bioelectrochemistry, bioremediation, environmental biotechnology, renewable energy generation, microbial electrosynthesis for value added products generation. He is also a recognized guest editor on special issue Sustainable Biotechnologies for Food, Fuel, Environment for Energy Nexus and various other reputed journals. He also has life memberships in BRSI and Institute of Science, Engineering and Technology Research. He also has a membership in World Research Council for the year 2019 to 2020. We are very honored to have you here with us, sir. With immense pleasure, I would like to call upon Dr. C. Nagendra Reddy to enlighten us with his knowledge on biorefineries, current prospects, and future perspective and microbial biofuels. Over to you, sir.
Thank you. Good evening, everyone here. I'm Dr. Nagennath, and thank you, Ms. Sangamitra, for the kind introduction that you have given about me. And firstly, I would like to thank Dr. Gopinath from VTHT Engineering College and AACT for giving me this opportunity to share my research experience with you all. And on this tiring day, I would like to brief you about the experience or the research activities that I've carried out during my entire PhD, postdoc, and during my assistant professorship also. And I'd like to explain you briefly, like in terms of what I have done. The thing is that I've completely worked on bioremediation of waste pollutants. I'll just share my screen here. Sir, is my screen visible, sir?
Yes, sir. Yes, sir. You can proceed, sir.
Yes. So I have completely worked on bioremediation of complex pollutants and also biofuel generation from both organic and inorganic carbon by using both bacteria and microalgae. And addition to this, I'd like to stress on the term integrated strategies. So these integrated strategies, when I say this would lead us to the biorefinery models. So which is our topic of interest today. So my topic, as I said, waste biorefinery models towards sustainable circular bioeconomy, current prospects and future perspectives, and also microbial fuels. So in this topic, I would speak very less about microbial biofuels because all the faculty here would have had experience on production of biofuels from various substrates or by using various pure and mixed microorganisms. So I would speak very little about microbial fuels, but more in detail explanation about waste biorefinery models. So, sir, with your permission, can I talk about microbial biofuels first, followed by waste biorefinery models?
No problem, sir. You can go ahead, sir.
Because first I'll talk about biofuels first, and after which I can
Yeah,
relate
yeah,
that to the
definitely.
waste
Maybe
biorefinery
that
models.
continuity will be there. Yeah.
Yes, sir. So in this, yes, yes. So coming to the energy. So what is most required today? Energy which is sustainable. So we do get energy from various fossil fuels, but you know the negative impacts of fossil fuel on the environment or the atmosphere. So we are the we are consuming the energy on a higher on a higher note than what is required because we are making use of it for each and every accessory we use or each and every gadget. So it has become an necessity for us. So when you see the slide here, the consumption of energy is increasing with respect to each year. So with the components of energy that we are using, the fossil fuels would be on higher note. Like oil is about 40%, coal is about 30%. So this has been increasing. So like oil, what we are using, like the fossil fuels, the energy from fossil fuels is 41 percentage, followed by electricity. It can be from hydro or like coal consumption, like 18%, natural gas 15, biofuels constitute to only 12%. Coal, peat, or shale is 10%, and other renewables is 4%. So, fortunately, our motto towards biofuel consumption is increasing, or utilization of biofuel for our necessity is increasing. So we have moved our we have moved towards the biofuel utilization. So we have a robust demand for these biofuels or renewable energy that we are talking about, and electricity generation using biofuels has been increased, and it would reach around 15 to 80 watt per hour in 2040, and it constitutes to around 55% of the total energy that we are consuming by 2030. And with the increasing demand of biofuel, so you know all the negative impacts of using fossil fuels, and the benefits of going for biofuels. So with this increasing demand, we also have increasing investments, which would increase GDP of our country, and like many international and national companies are coming forward to invest in biofuels, and we also have developed like suitable policies for that. And coming to advantage of these biofuels or renewables, so we are fourth in wind power, fifth in solar power, and fifth in renewable power installed capacity as of 2018, and we would be increasing these values or statistics with respect to each and every year. So one advantage of our country is tropical country. So we have like good sunlight, or our environment supports us to go for the biofuels or renewable energy. So we have renewable energy installed capacity increased to 226% in the last 5 years, and all the statistics that I'm showing you here give us great motivation or inspiration that we are going in a right way towards sustainable India. So market size is increasing like with respect to each and every year, and even the bio components that we are producing. We have different government initiatives as said by the like in the initial stage. We are shifting towards biofuel energy, and there are many policies coming up for the same. So you know what biofuels are, and these biofuels are four types. They're like first generation, second generation, third generation, fourth generation. So in first generation, we had this issue of food versus fuel. So that is why we have gone towards second generation. And this second generation, the productivity is very less. So we have moved towards third generation. In this third generation, we are using algae and its other components, like which are photosynthetic in nature, so that we get higher yield than the plant sources. So in fourth generation, we are moving towards like genetically modified organisms, which can give more yield than the current microalgae counterparts. So we have had many technologies to convert these substrates into biofuels. So they could be like physical, chemical, thermochemical, or biological. And the disadvantages with physical, chemical, thermochemical, you are like utilizing more energy, giving us secondary pollutants. But when we are talking about biological conversion, we have had the advantage of complete utilization of substrate, or more yield and less consumption of energy required for production of biofuels. So these are all different advantages when we talk about biofuels. So these biofuels, there are many technologies like composting, anaerobic digestion, fermentation process, and transesterification. So all these biological conversion technologies would lead us into production of biofuels without much requirement of energy. So for this particular no need of like much energy for the biofuel production, we'll be taking waste as substrate. So generally, when we consider a bioprocess, we have downstreaming process, fermentation, and upstreaming. Sorry, upstreaming, fermentation, and downstreaming. So in this upstreaming process, the substrate that we give for the microorganisms, so it should not have more value. So when we have more value, then the biofuel that is produced or the product that is produced from this microbial conversion process would also have high value. So in order to curb the value or the expenses of producing these biofuels, we are going for lesser value substrates like waste. So waste can be in any form. It can be like solid waste, liquid waste, or even gaseous waste. So solid waste, municipal solid waste, liquid effluents from various industries, and gaseous forms like flue gas, and also like carbon dioxide. So we are utilizing various substrates from these all these waste sources, and then utilizing them for production of biofuels, which would give us higher conversion ability and also less expenses for the production of this biofuel. So in this bio process, when we talk about three different steps: upstreaming, fermentation, and downstreaming. So in upstreaming, like we need to prepare all the components that are required for the bio process. So first one would be microorganism. So microorganisms, it can be a pure source or mixed culture. So when we talk about pure source, we need to have all the conditions required for carrying out the reaction. But when we talk about mixed culture for a bioprocess, then our system expenses or the bioprocess expenses would be cut down to more than 75%, because we don't have to maintain sterile conditions, and we don't have to go for the pure substrates. If it is mixed culture, then we can have any kind of waste as substrate. If it is pure culture, we need to specifically go for the substrate that we are using. So in this, the type of substrate plays an important role. Along with that, the microorganism, either it is pure or mixed culture, and in few cases we can also go for bio augmentation. For example, I go for a bioprocess which requires only few strains. So I would be utilizing one particular strain, for example, Pseudomonas, for production of bioelectricity by using glucose or acetate as substrate. But I would like to enhance the productivity by using waste. So what I do, I go for two different microorganisms, one for hydrolysis and another for bioelectricity production. So in hydrolysis, hydrolytic bacteria can be used to convert the complex materials into simpler ones. And these simpler monomers would be utilized by the electrifying bacteria or electroactive bacteria, so that they produce more amount of electrons, which is bioelectricity. So I can go for pure, mixed, or bioaugmented cultures. So microorganism, substrates, and various controls required for the fermentation process, along with sterilization, can be optimized in upstreaming process. Coming to fermentation process, so the substrate, uh, microorganism, and all the optimized conditions would be further reacted to form the product in the reactor or the fermenter. So after this, the product has to be separated from the media. So we have different mechanisms to separate the products from them. So I would be explaining you in next slides. So in the upstreaming process, inoculant development, preparation of culture media, and sterilization. These three components play a significant role to cut down the costs initially, followed by fermentation. And in the downstreaming process, we have product recovery, formulation, and its further polishing. So in upstreaming process, We go for optimizing the media that is required by the microorganism, and this media should have all the components like trace elements, inducers, precursors, repressors, anti-foaming agents, carbon, nitrogen, growth factors. So these are all required for well functioning of bacteria or so there are two kinds of media. First one is inoculation media, and the other one is production media. So in the inoculum media, we use a certain media which is good for the bacteria to grow. When we culture the media, so it should have the like optimum medial components, like carbon should be in particular concentration, or nitrogen, or like all the other trace metals. So this inoculum media is very important for the uh, culturing of inoculum, followed by production media. In this production media, we make sure the components required for higher production of product is made sure that is present in higher quantities. So in this culture media, we need to take care of all these components. It can be a pure substrate, or it can be a, waste form also. So in this waste, we should optimize again how much amount of carbon is there, how much amount of nitrogen is there. So is the bacteria able to like take up this amount of carbon? So we have this optimum carbon concentration, or optimum medial concentration for all the bacteria or all the microorganisms. So even the higher concentration of carbon would lead to a lesser productivity, or even lesser concentration of carbon would also lead to lesser productivity of the product. So we should make sure the optimal quantity is present in the media if we are going with the waste substrate. So sterilization, there are different sterilization techniques. So we need to make sure the sterilization is performed well for pure culture bioprocessing. So if it is pure culture, sterilization is most important. And even if we neglect a single spatula, or a single collection tube, so that would lead to contamination of complete media. So we have to take extreme care with this sterilization also. And so these are all various factors like pH, temperature, conductivity, concentration of carbon, NPK, and the inoculum concentration also. So if it is like 1,000 liter reactor, and if I give only 5 ml of inoculum to the reactor, so that doesn't serve the purpose. So it should be around 15 to 20% of total volume of the bioreactor. So in that case, we have to initially go with culturing of the inoculum. As I said, we have inoculum media. So we initially culture the media and then go for inoculating the bioreactor or fermenter. So there are various types of reactors: continuous T tank reactors, bubble column reactors, airlift, fluidized bed reactor, packed bed reactor, photobioreactors, membrane bioreactors, rotary drum bioreactors. So we choose what kind of reactor is required for the product formation. So if it needs to have uh, continuous stirring, we go for continuous stir tank bioreactor. Or if it is if it requires light to be like uh, uh, impedant on the reactor for the microorganisms, like microalgal photobioreactors, so we go for photobioreactors. So there are different types of bioreactors that can be used for various purposes, based on the inoculum that you take and based on the product that is formed. So we know like what this growth curve is, and this growth curve helps in taking the product in correct time. So this lag, log, stationary, and death phase. So our products would be produced more in the log phase. So when we draw this growth curve of a bacteria that we are culturing in the bioreactor or biofermenter, then it would be easy for us, and we'll get to know when to uh, like separate the products from the bioreactor. or else these products that are formed, or the like for example, our product is acetate. So when this acetate is present in the reactor for a longer period of time, even the microorganisms would feed on the acetate. So the quantity of acetate that is produced in the reactor would be reduced. So we should calculate or like draw this growth curve in order to like extract more amount of product. Followed by fermentation, we have different components that have to be taken care of for this proper functioning of fermentation process. So all the components. So when we go for scaling up, the lab scale and pilot scale. So for lab scale, we might require certain optimum conditions, but these are not directly related to the pilot scale operation. For example, if I take HRT, hydraulic retention time, to be 2 days for a lab scale reactor, which is around 1 liter or 5 liters, then it might not be the same for pilot scale reaction. So we have to optimize each and every condition when we go for scaling up of the bioprocess. So even the extraction time, hydraulic retention time, pH, even the pH changes drastically when the reaction is fully functional. So you pretty well know about different components of a fermenter. So all these components should be designed in a way to reduce the energy that is consumed during the fermentation process. So it can be introduction of like foam anti-foaming agents, or dropping of NaOH or HCl into the reactor. So we have to optimize. So in order to reduce the cost of this fermentation process in this particular fermenter components thing. Yes. And there are three modes of operation, so which is directly related to the product formation. So batch culture, I just give the inlet once and take the product at one time. Whereas in fed batch, like I continuously I give the substrate for a period of time, and I collect the substrate in a batch, in a like stepwise manner. Whereas in continuous culture, continuous mode of operation, the inlet would be given to the reactor continuously, and even the product will be extracted continuously. So we have different downstreaming process. In this downstreaming process, we have to focus on the product, whether it is an intracellular product or extracellular product. So if it is intracellular product, so I have to take extreme or like extra steps for disrupting the cell. If it is an extracellular product, I don't have to really worry about these cells. I can separate the products and cells. So the cost of downstreaming would be reduced when it is an extracellular product. If it is an intracellular product, I have to go for various cell disruption methods. It can be mechanical, physical, chemical, or enzymatic. So this addition of cell disruption would give us more like extra work and also extra expenses for the bioreaction or product. And after the cell disruption, we need to remove the insolubles by various techniques of centrifugation, flocculation, filtration, sedimentation, and isolate the product by using adsorption, evaporation, extraction, precipitation, membrane filtration. And after the product is isolated from the cell materials or cell constituents, then the product has to be purified in order to go for commercialization. So if insulin is produced, then like I need to purify it when it has some purpose, like medical purposes. Then I need to purify the product before going for the commercialization. So after purification, I make sure the product is in proper form. So I go for either lyophilization, drying, sterilization, or crystallization to make this product extra to have extra stability or longevity. So even the product that is produced should have stable shelf life. It should not be denatured during the transportation, or it should not be denatured when we have little higher temperatures, or when it is subjected to other open source formats. So various biofuels that can be produced or that are being focused by various researchers are biohydrogen, biodiesel, biogas, synthetic fuels, bioalcohols, biobutanol, biodiesel, and bioethanol. So these are various biofuels that are being produced from various technologies. So these technologies are being advanced with respect to the substrate, or with respect to yielding more amount of energy or more amount of product. So in previous days, it was only anaerobic digestion process that was used for biohydrogen production. But nowadays, we are also going for electrofermentation process. So we can produce electrofermentation biohydrogen or biomethane or bioalcohols by using this electrofermentation process. It can be microbial electrosynthesis or biochemical system. So based on different productivity levels. So biodiesel can be produced from microalgae by sequestering carbon dioxide from the atmosphere, or utilizing waste materials from the waste, from various effluents of industry. And biogas can be produced from anaerobic digestion process or electrofermentation process, bioalcohols. So this all these products or all the biofuels can be produced from various substrates. So these substrates can be pure substrate like acetate, butyrate, or propionate can be used for production of this biohydrogen, biogas, or bioalcohols. Apart from this, we can also use waste materials like effluent from dairy industry can be used to produce this biohydrogen, bio methane, or bioalcohols. And also we can also use carbon dioxide. So when this carbon dioxide is given to a certain bacteria, and we give certain potential for the bacteria to convert this waste material into biofuel, so it is like it is having more sustainability rather than going for the pure substrates. So when I talk about biofuel production, I have completely, as I said, I've worked on microbial fuel cell. So this microbial fuel cell, there are two, single chamber, dual chamber, and three chambered microbial fuel cells are also there. But when we talk about the mechanism of this biofuel, bioelectricity production using microbial fuel cell, there are two components: anode and cathode. So this anode and cathode, they have their own purpose. So when I talk about anode, this anode, it is mostly anaerobic in nature, and the microorganisms that are present in the anode chamber would feed on the glucose, and they convert the glucose into carbon dioxide, protons, electrons, and volatile fatty acids. So these volatile fatty acids can be used as platform chemicals for commercialization: acetate, butyrate, so lactic acid, lactate. So all these volatile fatty acids, they have their own value. Along with that, protons and electrons are also produced. So these electrons would be captured by the anode electrode, and they would be conducted into the cathode chamber. This cathode chamber is aerobic in nature. So the protons, electrons, and oxygen that is present in the cathode chamber would produce water molecule. So this is a process wherein we are converting the waste materials, the carbon substrates, into volatile fatty acids, which are having high value than the initial counterparts. So when we talk about single chamber, it's the same mechanism, but the cathode would be subjected to the atmosphere, air in the atmosphere, because it need to have oxygen for conversion of protons and electrons into water molecule. So this is already a process wherein the uh, see, for example, in anode chamber, I give 10 grams of glucose, and I get some around 6 or 7 grams of volatile fatty acids. Along with that, the protons and electrons are also produced. So this concentration gradient would trigger the movement of electrons into cathode chamber, because we use proton exchange membrane in between the anode and cathode. These protons would be moving from anode to cathode chamber. So the presence of proton in the cathode chamber would trigger the movement of electrons from anode to cathode chamber when the circuit is closed. So by this way, we are producing bioelectricity, and this can be stored when we produce in larger quantities. So this is complete mechanism of how a microbial fuel cell works. So this uh, glucose molecule that I've showed you in the picture can be in any form. So it can be carbon dioxide. So with the bacteria that can take up the carbon dioxide and convert the carbon dioxide into volatile fatty acids are also there. So I go for hydrogenotrophic methanogens, which would convert the carbon dioxide into methane gas. So the substrate type and concentration, inoculum type are most important in any biofuel conversion technology. So when I go for specific bacteria or specific substrate, then I can have the higher yield of a product rather than going for a mixed culture. So mixed culture doesn't incur more expenses. But when we target the product that is formed during the process, then it is much necessary for me to go for a specific bacteria. If it is general digestion process, then mixed culture is fine. So this I would explain you at the end. So biofuels, there is much gap between biofuel production and commercialization. So we need to bridge the gap between biofuel production and its complete commercialization. So in order to bridge the gap, I have devised SWOT analysis for this particular biofuel commercialization. And in this SWOT analysis, I got to know where this product or the biofuel that is being produced is having a strength, weakness, opportunity, or threat. So these are this table have devised for a paper that is being which will be communicated in a week's time. So in this particular SWOT analysis, there are different production different steps in production or in performance, in marketing, in different types of methods used or equipment that is being used. So we have developed this table for each and every category, and this particular table is specifically for photobioreactor or biodiesel production. So when we talk about production of this biofuel or biodiesel, then the common points that I get into my mind are land, climate, predators, raw materials, cost, manpower. So when I take all these components into consideration, the strengths would be less land. So when I use microalgae, the primary advantage is production of more biodiesel in less space. So, and also a few cheaper raw materials. So I don't have to go for pure substrates. I can use either effluents, or I can also go for CO2 sequestration. So based on the type of microalgae that I use, auto, hetero, and phototrophic, and less manpower is required for this particular microalgal biodiesel production. And coming to weakness, so climate would be a weakness for biodiesel production, because climate is unpredictable, and when I go for open pond system, so I need to take care of uh, certain aspects like contamination or predators which would prey on the algae, and also harvesting techniques, and also when there is higher temperature or when there is pH change in the medium. So I need to take all these factors into consideration. So these are all weakness. And coming to threats, so all these weaknesses, if not addressed, that would affect the productivity, and it generates unemployment, because we are using less manpower. That might be a advantage or disadvantage based on the situation. And when I talk about performance, so this performance in terms of efficiency, feasibility, availability, and compatibility. So efficiency, it is very effective, and feasibility, it is not expensive when compared to fossil fuels. So once the technology is developed from microalgal utilization, then this might not pose like this might not pose any much problem for production of biofuel. So right now, the difference between fossil fuel biodiesel, fossil fuel diesel, and biodiesel is not much. But in later stages of this technology development, that might bridge the gap. So not easily available. This biodiesel is not easily available. So this is weakness, and it's not compatible with the currently used vehicles. So when I use a diesel vehicle and I cannot go with diesel fuel, because the filters would get damaged, or the engine can also be damaged. But this, when I optimize, so there are certain countries wherein they are completely changing the engines just for biodiesel. So we will also adapt to these systems when this biofuel production is having more opportunity. So when I come to marketing, so awareness should be created. So this awareness that I'm talking about, so many people, when I say biodiesel, they would not go for it, even though it is around 5 rupees or 10 rupees lesser than the diesel, because they have this perception of these biodiesels might damage their engine, and they do not have proper awareness about the biodiesel. Both the diesel and biodiesel uh, would have equal performance, and there are certain religious beliefs, and these religious beliefs of going for unnatural things. So there might that might also pose a problem, and competition with the present fuels would be a weakness, and in future there would be more competition between various biofuels, not with the fossil fuels but various biofuels, and cost is advertising is costly. So when I talk about biodiesel, so I would set up a biodiesel bunk, and I would go for proper advertisement. I should go for proper advertisement, or else people might not go for biodiesel utilization. And coming to methods, there are different methods wherein I can use open and closed ponds, hybrid systems, and also integrated systems. So these open, closed, hybrid, and integrated systems also have strength, weakness, and threats. Coming to strength, open pond system, they are cheap and simple. Not much work is there to cultivate the algae in that. And in closed system, space would be a limiting factor. And in hybrid system, we need to have more expertise in handling hybrid systems, but the yield would be high. And in integrated system, we can go for cutting down the expenses. So I would use the waste as the substrate, and also certain mechanisms wherein the product expenses would be cut down to the maximum level. So these are the advantages, disadvantages of using biodiesel. And coming to equipment, we have different harvesting techniques which are more expensive than the transesterification process. So harvesting in a 1 liter reactor would not pose a problem. But if I'm operating some thousands and thousands liters of open pond or closed system, then that would be really difficult for me to harvest microalgae from the media or the wastewater. So like harvesting, it again requires like more energy consumption by utilizing different techniques, and also biomass processing. So the process, the biomass would also give us more amount of energy, and oil extraction and purification. So all this. So when I talk about diesel, so all this biomass processing, that would be limited. So refining of crude petroleum is very less. But when I consider biodiesel processing, I need to disrupt the cell wall. I need to like purify the lipids, and then go for transesterification. after transesterification, I need to check the components of biodiesel, whether it is in the normal range or not. And so this is a laborious process, wherein the optimization of all this process would give us biodiesel in a more simple way than what we are expecting right now. So this technology is what we are going for. It can be open, closed, hybrid, or integrated strategy. These technologies have to be like commercialized in terms of various technology transfers. So this technology can be measured by using TRL, so technology readiness level. So right now we are in the stage of TRL 3 or 4, but we need to go for TRL 8 or 9 in order to successfully develop biodiesel or biofuel. So this is completely about microbial biofuels. In my next topic, biorefinery, I would explain the biofuel production completely with respect to that particular model. So any questions up to this microbial biofuels?
Good evening, sir.
Good evening.
Yeah, myself, I'm Krishna Veni, Assistant Professor, Department of Microbiology from PSG College of Arts and Science,
Hello, ma'am.
Coimbatore.
Yes, ma'am.
Am I
Hello.
audible?
Yes, ma'am. Yes, ma'am.
Perfect. Sir, you were talking about the microbial fuel cells, fuel cell
Ma'am.
generation.
Yes, ma'am.
Yeah. Sir, you were also talking about the volatile fatty acids.
Yes, ma'am.
Should it be purified and taken, or the entire system is only on the electron transfer and generation of electricity, or are we also looking for byproducts with the volatile fatty acids and others?
Yes. Can I answer, ma'am?
Please, sir.
Ma'am, that depends on the requirement. Like, for example, if I'm talking about bioelectricity generation, my primary objective of the study is bioelectricity generation, then I would focus more on electricity like capture. If it is a production of carboxylate or platform chemicals, like it can be acetate, butyrate, lactate, propionate, then I would focus more on achieving these particular products from the bioreactor, I would say, and then like extraction, purification.
Sir, is the mixed culture giving better results than the individual cultures, or could you make any
In
comparison
terms
while
of, ma'am,
perform electricity generation?
Electricity generation, pure culture would give you higher electricity than with the mixed culture, because in mixed culture there are many microorganisms which would utilize the electrons that are generated for their own purposes.
Okay. So what was the scale you in which you had been testing this, sir? I'm interested in understanding how many liters of media you were using for the process of fuel cells, sir.
Ma'am, we have worked with 500 ml of a total working volume,
Okay.
and we have got around 3 millivolts higher currents
Okay.
than the normal reactors that were operated.
Okay. Thank you, sir. Thank you.
Yes, ma'am.
If any other further questions are there, you can unmute yourself. You can feel free to interact with the sir. Participants? Yeah, I think no other questions, sir.
So can I continue with the next topic, sir?
Yes, sir. Yes, yes, sir. Please.
Sir, just give me 2 minutes, sir.
Yeah, sure, sir. Sure, sure.
So moving on to the next topic of biorefinery models. So when I talk about increasing the standards of our living, so it can be in terms of urbanization or industrialization. So it can be anything. But what are the negative impacts of these terms that I'm talking about? For example, urbanization or industrialization. So that would be like giving us more flue gases or like concrete jungles. So all these are all negative impacts of the advancements that we are going with. So it can be population growth, increasing GDP, increasing income, high material consumption, high energy consumption, industrialization, resource consumption. In olden days, like we have not been using more current. There was no requirement actually. So we were going only for like fan, TV, or light. But now we have had many advancements or many technologies wherein we have smart technology for freezers, ACs, or even automatic dishwashers. So the consumption of energy has increased a lot with respect to the advancement. So what we are generating from this? So there are pollution, waste generation, economic overshoot, congestion, health impact, global warming, resource scarcity, and environmental imbalance. So these are all negative impacts of the advancements that we are talking about. So the technology that we are taking right now is take, make, and dispose concept. So I'm taking a resource, I'm utilizing it and disposing it off. So it is very unsustainable. So like for example, I take a paper. So paper is like produced from trees, and this paper, whatever I write, is being disposed of if the work is done. But right now we are also going for reusing or recycling, but it is an unsustainable way. So we have to look for a sustainable concept wherein the take, make, dispose concept is oriented in terms of reusing, recycling, or reducing the resource utilization. So the three R's concept. So this three R's concept, reduce, reuse, and recycle, would minimize the resource utilization and also waste generation from the process. So when you see the slide, linear economy, the resources are utilized for production of any product, they are consumed and waste is being generated. So this waste is again thrown back into the environment. So they are not utilizing it. So but coming to chain economy, in this chain economy resources are utilized, and we have a different process of like reducing also or reusing also in this chain economy, but waste is generated in little quantity. So in linear economy, waste is completely disposed of, whereas in chain economy, the waste is generated but not as good as this linear economy. So this chain economy is better, but not the ideal one. But when I talk about circular economy, the waste products that are the waste that is generated from the chain economy is reutilized in the process, so that there is no waste produced and also there is no resource utilization. So by this way we are closing the loop. So this particular closing the loop would help in minimizing the resources, or putting more stress on the environment. It can be in terms of resources or it can be in terms of waste generation. So in circular economy, production and consumption systems are designed in a way that products and waste materials are reused and recycled within the production and consumption system. So this is how our circular bioeconomy is going to impact the environment. So in earlier perspective, waste and energy, they go in different ways. But right now, waste and energy production, they go hand to hand. So when there is waste generated, then that particular waste can be utilized for production of energy or various biochemicals. So these biochemicals can be in various forms. So whatever we call, like for example, you talk about omega-3 fatty acids. These omega-3 fatty acids are obtained from like fish. So this fish have to be like sacrificed, and then these omega-3 fatty acids have to be purified and sold as capsules. But these omega-3 fatty acids, but they're produced from microalgae. These microalgae are utilized by the fish, and this fish get the omega-3 fatty acids. That is how we are capturing the omega-3 fatty acids right now. But when we talk about this omega-3 fatty acids, we don't have to rely completely on environment. We can also utilize certain bacteria or microalgae to produce omega-3 fatty acids in a lab, so which is economical and sustainable. So we have this sustainable waste management in present scenario. So this waste can be like can lead us to produce bioenergy and biochemicals by various treatment strategies, and we have dual benefits from it. No food versus fuel energy issue, ecologically renewable, environmentally sustainable, and it advocates biorefinery concept, and it has lower carbon footprint. So these are the advantages of going with closing the loop concept or biorefinery concept. So these are various wastes that are produced. So urban solid waste is around 1247. This urban solid waste has a scope to produce 1247 megawatts of energy. So urban liquid waste, it has 375 megawatts scope of energy potential. Paper liquid waste, so from paper industry, so it has 254 megawatts energy potential. So these are various effluents or waste products that can be that has the scope of producing energy, and this all these wastes would constitute to produce 5690 megawatt. And this information has been taken from MNRE, and this is how we can look forward to utilize waste for our waste bioremediation process and producing biofuels. So biorefinery concept. So in this so what is a refinery concept? So what is a refinery? So in refinery, we use crude material, and then we refine them into certain products. But during the refining process, we are producing various waste products. It can be like they can be toxic, recalcitrant, or they can also be persistent organic pollutants which cannot be like degraded in a certain time. So that is why we are going for biorefinery. So in this biorefinery, we use waste as feedstock, and we produce various products. It can be fuel, it can be power, it can be chemicals, it can be food, it can be feed, it can be fertilizer, and also heat energy is being generated. So this triangle represents 3 R's: recycle, reduce, and reuse. So this utilizing the biorefinery concept would be a next big thing for all the sustainable technologies that we are developing, not only in biological field, even the other fields that are going for advancements in their respective strategies. They are also looking for closing the loop approach. So they are not ready to throw the waste, because that waste generation is one aspect, and treating the waste before they are dumped into nearby water bodies or nearby dumping yards is another aspect for them. So the government has made mandate for this waste that is being generated for proper treatment and disposal, or like sending back into the environment. So we need to completely focus on the waste that is being generated or that is being utilized. So there are different waste biorefinery models. So they are acidogenic model, carbon dioxide sequestration model, photosynthetic model, bioelectrogenic model, and nutrient model. So these are different waste biorefinery models, and these waste biorefinery models. So based on the requirement. So if I use acidogenic model by utilizing various bacteria, I can produce biohydrogen, biomethane, biogas, or bioalcohols. So that depends on type of substrate used and type of organism that I'm using. And when I talk about carbon dioxide sequestration model, I can produce biodiesel and also platform chemicals, volatile fatty acids, as I said. And photosynthetic model, I would use carbon dioxide and also light energy to produce various pigments, fatty acids, and biodiesel. And in bioelectrogenic model, I use waste materials for production of bioelectricity and also precursor molecules. And in nutrient model, we go for production of in nutrient model, we are not going to like discard the nutrients that are being present in various effluents or wastewaters. So I'm going to reuse or recover the nutrients from the wastewater and utilize that recovered nutrients for various purposes like biofertilizer or feed and fuel production. So first one is acidogenic model biorefinery. In this acidogenic model biorefinery, the substrate that I'm giving to the bacteria would be converted into various products. So the conversion would require again hydrolysis. So there are four steps in an like anaerobic digestion process. Hydrolysis, acidogenesis, and methanogenesis. So in the first step, the hydrolysis, the complex polysaccharides would be converted into simple monomers by the process of hydrolysis, and there are certain bacteria, hydrolytic bacteria, that would act on the polysaccharides or complex materials and convert them into simple sugars. And these simple sugars are utilized by acidogens, acetogens, or methanogens to produce various products. So we need to have combination of various strains when I'm going for complex pollutant utilization. So in acidogenesis, I get various platform chemicals, hydrogen, carbon dioxide as end products, and these monomers can also be utilized for production of like acetate through acidogenesis, and all these end products from acidogenesis and acetogenesis can be utilized to produce methane. So these products that I'm the substrates that I'm using can have various products formed based on the microorganism or based on the conditions that I provide for the microorganism. So if the conditions that I provide are making the pathway to go towards platform chemicals, then that would be feasible for production of lactate, butyrate, and all. But if I'm changing the pH or other conditions to go towards biogas production, then that would be different case. So in this particular acidogenic model, whatever the waste that is being produced is being utilized in another way and in another process to produce higher amount of products. So food waste example is food waste is used by the bacteria through acidogenesis process, and biohydrogen is produced, and the volatile fatty acids that are produced simultaneously with biohydrogen or biogas would be utilized for biomethane production or biopolymers, PHR, PHBs, or biodiesel production or bioelectricity production. So the end product is not limited to biohydrogen or volatile fatty acids produced. So that can also go towards final end products, and these final end products can be having more value than the substrate or the primary products. So C2, C3, and C4 products might not have higher value than biopolymers, PHAs and PHBs, which are bioplastics or biomethane. And this biomethane and biohydrogen can be blended in a way to produce biohydrogen. So this biohydrogen production involves the balance between different microorganisms and retention time of the media in the reactor. So the food waste that is being used is producing various biohydrogen, four carbon compound, volatile fatty acids, and three carbon compounds. And as you see in the picture, so various different strategies are photosynthesis can be utilized by microalgae or photosynthetic bacteria. They can utilize the volatile fatty acids and produce different compounds, and also these compounds can be moving towards methanogenesis. where methanogens are present in the reactor in larger concentration than the acidogens, and these volatile fatty acids can be utilized as substrate in microbial fuel cell to produce bioelectricity, and bioanoxygenase process to produce PHAs or PHBs. And these astrogenic model has advantages in terms of environmental point of view, social point of view, and economical point of view. What way? So in environmental point of view, I'm reducing the amount of waste that is being discarded, and also I'm reducing the amount of green gases that are produced by normal anaerobic digestion process. And in social point of view, so I'm not completely relying on food sources for biofuel production. So I'm not going with a Jetropa or any other plants for producing this biodiesel. And in economical point of view, this the waste that I'm taking as a substrate has zero value. It is having zero value. So the product that is being produced, so when raw material is costly, then the product would also be costly. If the raw material is having zero value, it is waste. So waste is a waste that cannot be used. But in my case, I'm using this waste so that I can produce a product which is having a value. So I'm closing the loop in such a way that the waste is entering the loop and it is not being discarded. So apart from biohydrogen, short chain fatty acids, and bioalcohols, I can also go with different processes like chain elongation, alcohols production, hydrogenation, bioanoxygenesis, methanogenesis, microbial fuel cell to produce bioelectricity, photofermentation process, esterification process, carboxylate salts, and microalgae can also be used to produce bioplastics, hydrogen, mixed alcohols, long chain fatty acids, biofuels, bioelectricity, methane. So these are all the bio-based products that are being developed or produced from acidogenic model biorefinery. So the products are having high value because it is a biological process. So I don't have to use any chemicals or energy to give any potential for the organism to produce a product. So it is all a natural process in a controllable way. So I'm utilizing natural organisms in a controllable way so that I get varied composition of products. So in next model, so we have a carbon dioxide sequestration model. So in this carbon dioxide sequestration model, bacteria can sequester carbon dioxide, algae can also sequester carbon dioxide. So I would talk more on algae. And this algae, see, so in this process that I have I have used different types of wastewaters as organic carbon and also atmospheric carbon dioxide as a substrate for the microorganism. And after growth phase and starvation phase, I can use the biomass that is being harvested for production of biodiesel. So I get both biomass and lipid like biodiesel from utilizing wastewater and carbon dioxide from the atmosphere. So I've used different dye wastewaters in different compositions, design synthetic waste by using acetate in both growth phase and starvation phase. And in one reactor, in one experimental variation, I've used this design synthetic waste plus raw dye. And in third experimental variation, I've used design synthetic waste plus biofilm reactor effluent. So this is an integration strategy. So this the effluent that is produced from one bioreactor is used as substrate in this carbon dioxide sequestration process with microalgae. So in fourth experimental variation, I've used both biofilm reactor effluent in both growth phase and starvation phase. So this has showed an like immense and very like interesting results. So I could produce both biomass, I could produce biodiesel, and also treat the wastewater. So cell density is like higher with DHW plus DHW followed by DHW plus raw dye. So this is what I have achieved, like DHW plus raw dye. And the biofilm effluent reactor is also a good substrate for the microalgae. So as you can see in the picture, so all of this has very little variation. And coming to lipids, so lipids normally in starvation phase, so when I limit the concentrations of nitrogen, then I get higher amount of lipids. But the dye that I'm using is nitrogen dye. It has N double bond N in that. So the nitrogen compounds that are present in the effluent would limit the production of lipids, but it is comparatively less. Even though the lipids that are produced is in less concentration, I could get some amount of lipids when compared with the control operation. So DHW plus DHW, the first experimental variation showed 21% of lipids, followed by DHW plus radii. It is 18%. So the difference is only 3%. So in another model, I can use microbial fuel cell again. In this microbial fuel cell, as I said, in anode chamber, it is strict anaerobic in nature, whereas cathodic chamber, it is aerobic in nature, because it has to have oxygen to convert the protons and electrons into water molecule, or else this electricity passage would not be there. So that's why I use microalgae in cathode chamber. So it is just another integrating strategy. So in this integrating strategy, I'm using algae. I'm not using any air pump to provide oxygen. So I'm using algae. This algae would utilize the waste material or carbon from industries. So from industries, we are providing CO2 into the cathode chamber, so that these algae in the cathode chamber would utilize the CO2 and produce oxygen. So this oxygen would be converting the protons and electrons into water molecule. So this is how I have integrated the carbon dioxide sequestration model in microbial fuel cell. So this wastewater is rich in COD nutrients. So for this anode chamber, I can use one effluent, and in cathode chamber also I can use one more effluent. So in this case of microbial fuel cell and carbon dioxide sequestration, I'm using two different wastewaters for easy running of process, and also production of algal biomass and treated water. So wastewater is being treated and algal biomass is also being produced. So this treated water can be utilized for various domestic purposes, and algal biomass can be utilized as lipids for biodiesel production, or substrate for various anaerobic digestion process, for biogas production, biofertilizer production, bio oils, and adsorbent. So the de-oiled algal biomass can be an very good adsorbent. And this algal biomass can also be used as food supplement for humans and fish feed. And they also produce high value products like pigments, carotenoids, nutraceuticals, bioactive components. And low value products could be proteins and carbohydrates. So I'm not throwing any waste into the environment. So all the products are having some value from the waste. So I'm closing the loop by not throwing any waste into the atmosphere, or utilizing some resources. So here they are not resources. So I'm not going for any resource utilization. So I'm just producing bioelectricity, algal biomass, and treated water by utilizing waste materials and producing all these products in algal biorefinery. So in this, so one more experiment is on trace metals concentration on production of biomethane. So in this experiment, I have taken a single chamber reactor, and I've used inorganic carbon, which is carbon dioxide, for production of biomethane. So, but this work has been done by various scientists. But in this work, I have studied the impact of trace metals like cobalt, manganese, iron, magnesium. So these are all different trace metals that are having high impact on functioning of biocatalyst. So this when these trace metals are not there, we have reduced performance. So biogas composition, like I've studied biogas composition, and also various like dissolution of carbon dioxide into the media. So with the optimal concentration of all these components, I have got very good conversion of inorganic carbon into biogas. So the present study proposed and demonstrated the influence of trace metals on generation of biomethane by utilizing carbon dioxide as feedstock, and methane generation showed threefold increase when optimal concentrations of trace metals were used for the operation. So when optimal concentration of trace metals are used, I have got 3 times more productivity than the control operation. So these trace metals, when we give in very less concentration, these are not very well required by the microorganism. No, it is not true. So we need to have optimal concentration of trace metals, which is very much important for proper functioning of a biocatalyst or microorganism. So in another study, this study I have performed this in South Korea, Kyungju University, and this work has been done in Hong Kong Baptist University, Hong Kong. So in this, it is also an integrated strategy. So there are USB reactors in the lab that I have worked in, and the effluent from the USB reactor is utilized for the anode chamber of microbial fuel cell and anode chamber of microbial electrochemical cell. So so this effluent is utilized and in the anode chamber. But in MEC, we are overcoming the barrier of producing biogas from carbon dioxide. So this requires certain potential, certain potential for overcoming the barrier of thermodynamics. So what we have done, the electricity that is produced in the MFC is integrated with the MEC. So I'm not using any power source for operation of this microbial electrolysis cell. So I'm just using the energy from the microbial fuel cell. So I've used waste from the USB. I've used carbon dioxide from the USB. I've used bioelectricity from the MFC. So there is nothing which is costing me more or which is putting stress on the environment. I'm utilizing all waste materials in this to produce more amount of methane from carbon dioxide. So we have got higher methane production. So it is 93.4% of biomethane is produced from 6 gram per liter concentration of COD from this UASB. So the upgradation was from 60%, it is 93.4%. So we have enhanced around 33.4% of biomethane in the biogas composition. So in another carbon dioxide sequestration model, this is the overview of how the carbon dioxide can be utilized. So carbon dioxide from atmospheric carbon or industrial carbon dioxide can be utilized in biochemical system. So where low carbon compounds and high carbon compounds are produced, and this carbon dioxide can be utilized. There is another from microbial fuel cell. We also have plant MFC, which is utilizing the rhizobacteria that is present in the root zone of plant to produce electrons, and these electrons would be captured for bioelectricity generation. So this carbon dioxide can be used by the plant MFC to produce bioelectricity, and they can also be utilized by photosynthetic bacteria to produce various. They can also, these microalgae, as I said, they have various advantages produced from, and all this again can be integrated. So the microalgal biomass that is produced can be utilized in astrogenesis process to produce volatile fatty acids like hydrogen and methane, and volatile fatty acids can be utilized as biofertilizer, and they can also be utilized as nitrogen source microalgal biomass. And these can be integrated approach of utilizing the waste produced in one process as substrate in another process. So we are not relying on environment. Photosynthetic like by microalgae or photosynthetic bacteria. These reactors can be utilized. So these reactors also have very good impact on the commercialization process. So when I'm going for open pond, so the expenses would be less and productivity will be high. When I go for integrated strategy, in integrated strategy, I need to spend some money on integration of various processes, but the ability would be high. The productivity would be high. Sorry. So in this photosynthetic model, I use inorganic carbon dioxide or organic carbon in wastewater and nutrients in wastewater as substrate to the algae. And in algae, CO2 would be sequestered, biomass would be grown, COD would be degraded, and nutrients would be uptaken. So for each and every waste, we have one advantage in algae or photosynthetic bacteria. So carbon dioxide sequestration from the atmosphere or industry, and COD degradation in wastewater. So any wastewater would have some organic carbon in it. So that would be utilized by the algae by heterotrophic mode of metabolism, and nutrients that is present in wastewater, NPK. They would uptake the nutrients, and all this would increase the biomass, and this biomass would generate oxygen, biomass, and treated water as primary products. And in secondary products, as I explained, with like water can be produced, and with processing we have biodiesel, polyunsaturated fatty acids, omega-3 fatty acids, pigments, nutraceuticals, de-oiled biomass as substrate. And without processing, this algae as such can be utilized as biofertilizer, food, feed, and substrate to various anaerobic digestion processes. And treated water can be utilized for domestic or irrigation purposes. So this is here I have told you like with processing and without processing. So with processing, like there are different technologies again. So there are chemical conversion process for converting the biomass into biodiesel, and biochemical conversion process for converting the biomass or de-oiled algal cake into like biogas, biohydrogen, ethanol, biohydrogen again. And in thermochemical conversion, the de-oiled algal cake. So the biomass that is produced would be processed for biodiesel production. So after biodiesel production, the cake, the de-oiled algal cake, can be again further utilized by various technologies for producing various products again. And the wastewater that is being produced can be utilized for microalgal cultivation again. So in this biorefinery approach, no waste material is produced. So we have algal biocrude, polyunsaturated fatty acids, pigments, bioethanol. So these are all the products that are coming from the photosynthetic model biorefinery. So coming to our next nutrient model biorefinery. In this nutrient model biorefinery, as I said, the nutrients are recovered from the waste. We are not reducing the nutrient concentration in the wastewater. We are recovering. We are adding advantage. We are adding value to the recovered nutrients. So in this, I have taken. So this is also an integrated strategy. So I have operated a bioreactor with dye wastewater, and after operation, the dye concentration has been reduced to certain level. So after dye concentration has been reduced, the N double bond N would be converted into any of the nitrogen forms. It can be nitrate, nitrite, ammonia. So this nitrate, nitrate, and ammonia can be utilized as biofertilizer for farming purposes. And COD can be utilized in the anode chamber. So this is one more advantage. In this process, the dye effluent is given as substrate in the anode chamber, and this anode chamber would take up all the nutrients, would take up all the carbon that is present and convert them into VFAs, like carbon dioxide, protons, and electrons. So in this cation, so I have changed the membrane here. So initially I've used proton exchange membrane so that only protons can be exchanged from anode to cathode. But in this process, I've used cation exchange membrane. So in this cation exchange membrane, this transfers the cations. It can be like ammonia. So the ammonia that is being separated from the wastewater can be utilized for farming purposes. So we have got very good results from this experiment also. The control is like normal water we have used, and anolite, catholite. So germination we have studied, shoot length, root length we have studied, and ammonical nitrogen with respect to each anode and cathode chamber with respect to different R's has been evaluated. So we have got very good results, and we have separated the ammonia without any filtration or membrane filtration or any separation process. So we have just used biological process in order to produce biofertilizer out of this effluent. So this is like very good example of integrated strategy to recover the nutrients from the wastewater. So nutrient-rich wastewater can be from any industry or any bioprocess. So this they can be utilized in various physical process or chemical process, but our main focus is on biological process. In this biological process, there are different techniques again, like constructed wetlands, photosynthesis process, biological oxygen process. So in biological oxygen, photosynthesis process, I would use microalgae, aquatic ferns, plants uptake to recover the nutrients C and PK, and these nutrients can be utilized as animal feed, biofertilizer, biodiesel, bioalcohols. So this is the advantage of utilizing the biological process without inputting any energy. So apart from microalgae, I can also go with azolla or duckweed. This azolla and duckweed also gives very good results along with the microalgae when we are using for nutrient model biorefinery. So in our next model of bioelectrogenic model, as the name suggests, we are producing bioelectricity by utilizing various substrates, and there are different microbial fuel cells that can take up the carbon dioxide and produce various products. So based on the product produced, for example, my primary focus is on bioelectricity generation. So my objective would be microbial fuel cell. So fuel generation. So if it is treatment, so I would focus on biochemical treatment. So my focus is completely on treatment in this, not on electricity generation. Reactors are same, but the focus or the objective of the study varies with respect to the product or the substrate. So when I go for biohydrogen production, so I go for microbial electrolysis cell, sorry. So MEC. So my main focus is producing biohydrogen by inducing certain potential to the microorganism. And when my focus is value-added products like platform chemicals or other commercialized products, then my focus would be on bioelectrochemical system, BES. So different types of MFC reactors: benthic MFC, submersible MFC, plant MFC, stacked and multi-electrode MFC, photosynthetic MFC, hybrid and integrated MFC. So these are different types of MFC, and based on the objective, it is classified into 4 types. So I have already explained you about this mechanism of how the MFC would be operated. So I use different ways into the microbial fuel cell or any MFC, MEC, BES or BET. So vegetable and fruit waste, mixed kitchen and canteen waste, fruit processing wastewater, fermented food waste or wastewaters. So this I have taken from one of my papers on food waste MFC. So in that particular paper, I've completely focused on utilizing food substrates as input for the microbial fuel cell. So these food substrates would be converted into monomers, and these monomers would be utilized by the bacteria in the anode chamber, and they produce electricity, and in some cases biogas would also be produced, and the waste would be converted into biofertilizer. Carboxylic acids can be produced, biofuels produced, biopolymers, platform chemicals. So this is like a conversion of food waste into various products, bio-based products, I would say. So because our main focus or interest of our research is bio-based products, I go for this. So as I said, so these are different bioelectrogenic technologies: MFC for electricity, BET for treatment, BES for various products production, MEC for biohydrogen, and MDC, microbial desalination cell. So when I have high salinity wastewater, then I go for desalination cell by utilizing microorganisms. So in this, the ions would be separated based on the cation exchange and anion exchange. So the water would be like completely removed from these ions. So desalination takes place with the help of microorganisms, and it is sustainable one. So normally when we have some membranes or when we have some filters to separate the ions from water, it would cost me more. It is not sustainable also, because the membranes or filters have to be discarded at the end. But in this, the microbes are being developed, and these microorganisms have another scope for input as substrate in another process. So domestic effluent, industrial effluents, acidogenic integrated effluents, carbon dioxide, saline wastewater can be utilized in these biogenic technologies to produce these bio-based products. So this is holistic biorefinery approach. In this holistic biorefinery approach, I have integrated all the refineries into one. So this biorefinery approach that we have studied would help us in resource recovery in terms of NPK and bioeconomy by producing various bio-based products which are of high cost, like omega-3 fatty acids, platform chemicals, biodiesel. So these are very high value and this is sustainable. So we need to like completely focus on treatment. So we are not inputting any resource into the approach. So it is sustainable. So other studies I've already explained you. Yes. So the primary concept of biorefinery is reduce, reuse, and recover. So the three R's that play a significant role in biorefinery approach. So the biorefinery concept would help us in reducing the waste or complex pollutants in the waste and reuse the bio-based products or biomass that is obtained or treated water can be reused and recover. So we can recover various nutrients, electricity, bio-based products from this particular process. And it is like closed loop approach with zero discharge. So no discharge is being obtained from this biorefinery concept. So I would like to thank Dr. S. Venkat Mohan from CSR, Indian Institute of Technology, my PhD guide, and our principal P. Ravinder Reddy Garu, and Rajeshri, head of our department, Bukimin, my postdoc guide, and Professor Jonathan Wang, my postdoc guide, and Dr. Gopinath, and also the colleagues and fellow research scholars. Thank you, and I'm open to questions.
Thank you very much, sir. No, you are touched like every corner of the biotechnology. No, it is really interesting. It started from the basics of microbiology to the growth curve and all over all the other biofuel production and in biorefineries, and then other what are the value added products that can be obtained through biorefineries. So many topics that you have touched. So it is very interesting. I think participants, you can unmute yourself and also discuss with.
So that's why I've requested to start with microbial biofuels, so that I can continue with the algal biorefinery.
Yes, sir. Sir.
Fortunately, I've worked on many of these models, sir.
Yes.
During my PhD and postdoc studies. So
okay.
I'm
it is very interesting, actually. Actually, I worked in different area like environmental microbiology, like wastewater treatment, and purposely my PhD area is like air pollution control. So biological filters.
Sir.
And now I am eagerly wants to shift over from the the air pollution control to bioenergy production.
And sir, we'll have a collaboration, sir.
Yeah, definitely. Participants? Yeah, ma'am. Please, ma'am.
Thank you, Dr. Nagendranath, for a clear, detailed explanation. You gave a complete insight into the biorefinery process. Sir, I'm repeatedly keen in understanding the practicality of this. Usually in India, because you have a postdoc experience from your from your talk, I can understand. In India, usually we grow algae for biomass.
Yes, ma'am.
And a little for a fuel generation, sir. Is there a holistic approach for carbon dioxide sequestration, for, as you said, for other applications, what you had been mentioning, on a holistic utilization of algae? Is there this kind of an approach being done practically on a larger scale, other than the laboratory scale, in some industries?
Ma'am, in Reliance Industries, Mumbai, scientists are working on this particular approach of utilizing the waste and producing various bio-based products, ma'am.
Okay.
So,
So
on a larger scale,
are they using it for waste treatment and for
bio-based products production. Yes.
Okay, biomass production and carbon dioxide sequestration, all these
Yes, ma'am.
together using algae? Okay.
Yes, ma'am. Yes, ma'am. On a larger scale, and if it is in a lab scale, many researchers are working on this,
Yes.
but they could not go towards the commercialization or pilot scale studies.
Yeah, that is my curiosity, because
Yes, ma'am.
many a times when we work on biofuels with algae particularly, we are able to succeed in laboratory scale, but then scalability is the problem.
Yes, ma'am. Because our expertise would be only on one area. So I would focus on it more rather than the other areas. So when it is an industry or some company, they would hire some 3 or 4 experts from various like areas, so that they would integrate into a final biorefinery approach. Because me being like working on bioremediation, I would focus mostly on remediation of pollutants.
No, that's what I can understand from your
Yes,
talk.
ma'am.
See,
Yes.
we will concentrate only on, say, waste removal.
Yes, ma'am.
That will be the part of work, and we may not work on the circular economy concept actually.
Yes.
You know, taking it to the complete product generation, or profile of a larger products, as you had explained. So I was just curious to understand if in reality, are there some industries who are working on it?
Yes, ma'am. Yes, ma'am.
Thank you so much, sir.
No, actually, ma'am, Krishnavati ma'am, recently the Indian Oil Corporation has signed the some of the document with the Ministry of Petroleum that they are going to kickstart the biorefinery industry.
Okay.
I think already this has been initiated, but the exact location I forgotten.
Okay.
So
I think it should be Faridabad, sir.
Yeah, recently it was happened.
It should be in Faridabad.
Okay. Yeah, right.
Yes.
So probably this commercialization of this biorefinery means this was integrated, like waste lignocellulosic material to the conversion of biofuels. So in such a way that if they are established, means there is a scope for the other state, they may be taken up the project. I think so. So how the nuclear one side is the how energy is harvested in such a manner, definitely they will focus in this particular part.
And even our government is encouraging all the researchers in terms
yes,
of
sir.
Dirac-based projects or other CRG products to come up only with carbon dioxide sequestration models. Sir.
True.
So earlier, before 1 week, there was a call on Dirac Pace for developing a model for carbon dioxide sequestration.
Yes.
So it is like we do have so much encouragement from the government.
Currently, there is a call on the hydrogen platform also, sir. In
Yes.
So.
Okay.
So people who are like in this forum, if maybe concentrate on for your DSC, CRG. I mean probably by this January or February, next call up will be open. So if you focused in the area of like carbon dioxide sequestration using algal or otherwise biorefinery or integrated, what you say that the bioeconomy,
So picture concept, it is integration would play a significant role, sir. It would
Yeah.
add more value to the process that we are working on.
Yes, sir. And moreover, you need to supposed to concentrate on the development of products. So in this aspect, if you going to work on it, definitely we can able to get the fund. There is no doubt on it.
What is the algae that you are working on, sir? Particularly,
ma'am, I have worked on mixed culture, ma'am, because my focus was to reduce the economics behind this remediation. Because I cannot go with pure culture and treat a wastewater, because wastewater would again contain so many contaminants in terms of biological.
Then, in that case, is it microalgae, or you source it from the marine algae?
No, it is microalgae. Freshwater algae. Freshwater algae.
Okay. Do you do a characterization, or you don't do a characterization at all?
If
You just
we get,
roughly crude
no,
utilization.
ma'am. If we get significant results from the research, we would go for characterization.
Yeah,
If it
perfect.
is normal one, then we would not spend on characterization.
Time
of the
required, not required, not required.
True, ma'am.
Very nice. Thank you. Thank you, Dr. Nagendra.
Thank you, ma'am. Sir, so can we wind up the session, sir?
Sir, please, sir.
I think comparing team, so you can move forward for the vote of thanks.
Yes, sir. The best teachers are those who show you where to look, but don't tell you what to see. With this, I would like to call upon Dr. A. Sai Ramesh, Associate Professor, Department of Biotechnology, to propose vote of thanks.
Thank you, Sangamitra. So it's indeed a great pleasure to have with us Dr. C. Nagendranath Reddy, who is an assistant professor from Chaitanya Bharati Institute of Technology, Hyderabad. Sir, we are very much delighted to have you here, and it was a very thought-provoking session of yours for the past 2 hours. So we are very much sure that the participants here would have been taking up many things from you, and they would incorporate the same thing in their research and all other activities that they are going to perform with this particular current topic on MFCs and MBF. So I personally thank, and also through the side of the department and the institute, we are very much thankful to you, sir, for your time and the space for sharing your knowledge here. Thank you, sir. And also thank the participants who were there with us for the past 4 days and who are going to be there with us for the next 6 more days. So your presence makes us everything. It is the complete success of the FDP. So I'm thankful to you, to the participants, and for the coordinators and the comparing team. We are always thankful to you. Thank you all.
Thank you, sir. It's my pleasure to share my research details with you, and I would be happy to collaborate with anyone who is interested in like my area of expertise.
Yeah, definitely, sir. Definitely, we'll do in future. There is no doubt in that.
Anytime, sir.
So thank you very much, sir, for giving your time and acceptance of invitations.
Anytime, sir.
Yeah, thank you very much, sir.
Thank you, sir.
So participants, there was a feedback link is posted in the chat room, so you can fill out the form for the day 4 feedback. And if you have any queries on your mind, you can unmute yourself and you can feel free and discuss with me. No, there is no issues. Jaya ma'am. Jaya ma'am. Thank you, sir. Thank you very much, sir.
Thank you, sir.
Good night, all of you.
Good night, sir. Bye, sir.